Okay, so you should have gotten the relationship that the mass is just always x plus 100. And so then what is our little amount of work? Little amount of work is force times distance. Okay, so if we've got x feet of strap remaining, so what is the work to move it up a little bit? So the force is m times g. M is, so this is, we're in metric units. So if you're in metric units and you have kilograms, you need to use mg to get weight or newtons for force, right? Weight and force are the same. So weight is a type of force. Weight is a type of force. So we want the weight force. So then times delta x, and then we got our mass is our x plus 100. G is 9.8. So that's our little bit of work. Okay, and then we're going to total up all the work from 0 to 25. Force times little bit of distance. That's a little bit of work. Sum all the work, sum it all up from 0 to 25. Super easy to solve. Questions? Yeah.
So I switched on my x-axis my 25 and my 0.
Okay.
So I ended up getting 125 minus x for my rate of change.
Yeah, if you have a different frame of reference, it's possible that you could do it a different way. So did you say x was from the top down?
Yeah. So I said 25 was at the top, and then 0 was at the bottom. And I still ended up getting...
So then you're saying x is from the ground up.
Yeah, so x equals 0 at the bottom, and then 25 meters.
Right, so you're saying your frame of reference is x equals 0 is the bottom going up. It's possible, yeah. If you do a different frame of reference, as long as everything else is consistent, it's okay. Yeah?
I split up the work, so I did the work of the beam and then the work of the strap, and I did them separately, so one of them was integral, one of them wasn't. Is that incorrect?
So you did the beam was a non-integral? Yeah, that's okay. That's okay. Yeah, that's fine. I don't have time to answer every individual question about what you did on the quiz. One more.
Why don't you add the 1
Okay, so here, this mass is taking into account the beam and the strap. So when it's at the bottom, when it's at the ground, the total mass is 125. You've got the 25 kilograms for the strap and the 100 kilograms for the beam, and then by the time you get to the top, it's just 100 all the beam and no strap. So this takes into account both the beam and the strap. When it's 25. When you're when you're at the ground, you have a mass of 125. When you're at the top, you have a mass of 100. So that relationship takes into account both the beam and the strap for any distance x down. I don't know if that answers your question, but yeah. Okay, let's move on. Okay, removing fluid from a tank. Removing fluid from a tank. This is the next kind of category of problems. But again, we want to think in broad terms when we're solving these problems. Could we solve a problem that's a different application using the principles, right? So it's more about learning the principles of setting up these integrals rather than I'm going to learn how to do tank problems, okay? So the first thing we need some facts. The density of water is 1,000 kilograms per meters cubed. So that's mass density. And so then weight density would be times G, right? So this is like M, but a density type of M, right? And then this would be like mg, but for 1 meter cubed, right? For 1 cubic meter. So it's going to involve the same thing that we saw before. When you're in metric units and you're given kilograms, you have to use M times G or MA to get weight, right? And that's in newtons. When you're in English units, it doesn't involve mass. So you'll always be working with just force units or weight units. You won't be given mass and need to change it to force or weight, right? You just have weight units. So you should have seen that in the examples for today's web work. That whenever it's English, you're already working in the unit that you want. You're working in those force units. If you're in metric units, you're often given mass, and you have to make that one calculation to give you the force units. That calculation being mg. Okay. All right, so then the total weight, so for an example, the total weight of an amount of water would then be your weight density times the volume, right? So whatever volume you have, you're going to multiply that by 62.5, and that'll give you the total weight of that amount of water that you have, right? It should make perfect sense. Weight density times volume is going to give you weight. Okay, so a circular above-ground pool has a diameter of 20 feet and a depth of 4 feet, and it's filled with chocolate milk, which has a density of 64.3 pounds per foot cubed. Little bit thicker than water, just a little bit. How much work is required to remove all the chocolate milk from the pool? So, as always, we want to have a good picture that's labeled with all the variables and constants. It's going to really help us orient ourselves and solve the problem. So an above ground pool is a cylinder shape like this. Okay, and so this is some new, so it's totally filled, right? To the top. This chocolate milk is blue. Some new promotion for kids, right? Blue chocolate milk. Okay, so it's filled all the way up, and we need the work to remove all the chocolate milk from the pool. So why isn't this just a force times distance calculation, right? So work is force times distance. We know that basic premise. Why is it not just a straightforward calculation of force times distance? What is it about getting all the fluid out of a tank that prevents us from just force times distance? Yes, sir. What's that? Okay, so fluid. So some fluid. Which fluid travels the longest distance? At the bottom, right? So whatever fluid is at the bottom is going to take the most work to get out of the tank because it has to go the furthest. And then as you move up, so then the work at the top of the tank will be less. In fact, the work at the very, very top will be how much? How much work will it take to get the very first top layer, thin layer, off? Has no distance to go, virtually no distance to go. So the fluid at the top of the tank virtually has work of 0 to get it out. So with that in mind, then what kind of elements are we going to be breaking this down into? So we still need to calculate some fixed amount of work for some part of the fluid in order to make progress, right? We've got to know, we've got to take some amount of fluid in there and be able to calculate the work using F times D. So what kind of elements are we going to have? What kind of element are we going to have that will be able to actually calculate a constant amount of work. So for instance, like an element might be like this, like a cylinder, like this way. So will I take some amount like that? Will I be able to calculate a constant amount of work for that kind of chunk of the fluid, that chunk of the chocolate milk? Will I be able to? They're saying no. Why not? Yeah. Right. She said that still has the problem of changing distance. At the bottom of this, I've chosen this element like a vertical cylinder. At the bottom, it's going to take more work than toward the top. So what do I need? I need some element for which I can calculate a constant amount of work. What will that be like?
Just like pancakes.
So like a pancake. What about a pancake of fluid? Right, because what is it about a pancake of fluid? Like a horizontal pancake, all of that fluid will travel the same distance. So that's what I want to do. I want to think about some typical layer of chocolate milk. And if it's thin enough, then we can consider it all of that moving the same distance. It's all moving the same distance. So all we need to do is get the force required to lift that. What is the force required to lift something? In general, what is the force required to lift something? What's that called? You should know that. The force required to lift something or hold it up. It's its weight, right? Weight is force. So this amount of work is the force or the weight times the distance. Now, the distance now is not going to be delta x. The distance now is going to be how far we have to lift that thing to get it out of the tank. So we need a frame of reference. So again, we'll say from the top of the layer will be x like this. So now, what's the distance is not delta x. What is the distance that we're going to have to lift that thing through to get it out of the tank? So what will the distance be to get that out? According to how I've done it, it's just going to be x, right? I need to move that thing a distance of x. So now the force is what? Force is its weight. And so to get its total weight, we have the density, and we're going to do the density times what? The volume. So we're going to have our 64.3 times the volume of the layer. And that will be the weight or the force. Okay, you do the volume. So you do the volume. Everyone, this is similar to what we've seen before. So what is the volume of a typical pancake of chocolate milk? You do it. Everyone should be able to do it. Compare with the person next to you. Okay, so we're calculating the the little bit of work for this pancake. So the volume is going to be for that pancake. So who thinks they have the volume of the pancake? Yes, sir. Okay, you said 1/2 pi. Go ahead. 10 squared. Delta x. What do we think? Agree? Disagree? Make a change? Yeah. She doesn't want the 1/2. So what is it that a pancake is what shape? A pancake is what kind of shape? Cylinder. Cylinder, right? It's like a flattened cylinder. So do we want the 1/2 for a cylinder? No. So almost perfect, just no 1/2, right? So it's going to be pi r squared is the surface area. And then, so notice, the delta x here comes into the volume, comes into the force. It's not the distance anymore like it was when we were lifting chains or stretching the spring. Now the delta x comes in because we're taking a really thin layer and it's part of the volume calculation. But that, right there, that's our little bit of work for lifting one typical layer out. So that's, what is that? That's the typical amount of work to lift one layer at a depth of x out the top of the tank. So now we're home free. Total work is going to be, we're going to sum up all the little bits of work. Okay, so x from what to what? 0 to 4, because it's filled up. Okay, so for these emptying a tank, the work is force times distance. The force is the weight of a typical layer, right? Typical layer, and that's going to be density times volume. And then the distance is however you set up your frame of reference. So it might change, but the distance now is not the little distance, but how far we have to get that thing to the top to empty it. Okay, questions on this one? Anybody? All right, so as a variation on this, suppose that this is a tank in the factory, okay? And there's a pipe. Okay, and we got to get the chocolate milk out, and that pipe is 2 feet. And we got to get all the chocolate milk out of the tank, and the only way to get it out of the tank is out through that pipe. How would the setup be different? Question? Yeah. Okay, good. So let's check our units. So I've got this was pounds per foot cubed, and then times volume was pounds. So this is all pounds. Nope. Yep. Nope. With the dx. So all that was pounds, and then x is feet. So our work for English units, our work is foot pounds. Foot pounds. It's not joules. So joules is Newton meters. So Newton meters in metric is joules. That's metric. And then for English, I don't think that there's an abbreviated version. I think it's just foot pounds. So when you add up all those little amounts of foot pounds, you're going to get a big amount of foot pounds, right? You're going to add up a bunch of little foot pounds. It's going to total up to the total foot pounds of work to get all that chocolate milk out the tank. Okay, so now are we good on the first setup? Okay, so now how would the setup of this be different if to get it out of the tank, it's got to go out to the top of that pipe? How would the setup be different? So think about that just for a minute. Talk with the person next to you. How would the integral or the setup be different if it needs to come out the top of that pipe? Okay, there'd be two different ways to change our integral. There'd be two different ways to change our integral to do this. Anyone have a suggestion? What's the first way that it could be changed? Yeah.
So it would be 2 plus x because that would be the distance you're raising.
So he wants to change this x here to x plus 2 and leave everything else the same. Does it work? So for any layer that we had before, it just has to go 2 feet further now. So instead of going a distance x, it would be going a distance of x plus 2. Does it work?
Was it the line that said that tube smaller than the thing?
It doesn't have anything to do with that. So it's just the distance of every layer of water that has to go. So moving something horizontally, theoretically, for our purposes, takes no work. Okay? Moving something horizontally takes no work because there's no resistant force for moving something horizontally. So the fact that it has to all gather over to the left and go up the pipe, that doesn't have any bearing. Just moving it up is what takes work against lifting it against gravity. Okay? So this works. This is perfectly fine. You can change the distance instead to x plus 2. The other thing you can do is what? Who's got another suggestion? You got the right idea, but so what about integrating from 0 to 6? That's the right idea, but it wouldn't be from 0 to 6. What would it be? So what you're talking about now is changing your frame of reference. Make this x. So call that x, say x star. So you'd be integrating from what to what? Not 0 to 6. Well, where's the first layer? All right, so where's the first layer if that's our frame of reference, x? X equals what? 2. And where's the last layer? 6. So it wouldn't be from 0 to 6, it'd be from 2 to 6. It'd be from 2 to 6. So you could either change the x to x plus 2, or you could integrate from the same thing as before from 2 to 6. Okay, questions before we do one more example. Questions on that? Okay, but that's more work, right? Because all the layers are going 2 feet further, so that the amount of work is greater. Okay, another example. Okay, so for this one, we've got a trough. A trough, it's like what horses drink out of. They have a trapezoidal, some of them have a trapezoidal cross section. Okay, and so then this goes back like this. Okay, and so the dimensions of this trough are 0.6 or 60 centimeters. 60 centimeters wide at the bottom. 100 centimeters here. 50 centimeters deep. And then 200 centimeters back this way. Okay, and it's it is half filled with water. Okay, and so we want, how much work will it take to get this, all the water out of this half-filled trough? So what is going to be our element of interest here? What is going to be our element of interest that we can calculate a little bit of work for? So work is force times distance, we know. So how can you describe an element? What volume element are we going to have that's we're going to calculate the little bit of work for? Is it a pancake? What's the shape of it? It's a rectangular. So even though it's trapezoidal in its cross section, if you just take one thin layer is going to be rectangular. It won't have a trapezoid shape. One thin layer of water will be rectangular. So the volume will be width times length times height. But why? How is this different than the pool problem? So this is different than the pool problem because at different depths, what happens? At different depths, what happens to our layers?
The size changes.
Yeah, which side?
The width.
Yeah, so this width is a variable. All right, so let's we'll make our frame of reference. We'll make x will be down from the top of that. So what do we need? So we need a relationship that gives us the width at any value of x. Okay, so this is what we talked about before. We need width in terms of x. So if this is the top, it's like our positive x is going down. And so we've got what do we have? So what is, when x is 0, what is the width? So we want to do this ordered pairs and build that relationship out of the ordered pairs. When the depth is 0, the width is. So we're gonna so all those dimensions are given in centimeters, but we're gonna be working in metric units, so we're gonna need meters. So that width is 1. When the depth is what? 1/2 of a meter. What is the width? That's our 0.6, right? So we've got x and width. The width of our typical element, this rectangular layer, depends on x. So we set up the relationship by getting some ordered pairs. When x is 0, the width is 1. When x is 0.5, the width is 0.6. And so we can get our this is 0, width is 1. Right, okay. And so then we've got 0.6 for the rate of change, minus 1 over 0.5 minus 0, which is negative 0.4 over 0.5, or negative 0.8. Did I do the math right? That's our rate of change for x and w with respect to x. 4/5. Okay, so then what is our relationship? The width is negative 0.8 x. In this case, it's going to be just plus 1 because at 0, it's 1, right? So when x is 0, the width should be 1, so we can just add 1. Okay, so what's our volume? Our volume is, width is our negative 0.8x plus 1. The length, this dimension, is the 2 meters, and the height is our delta x. So the force is all of that volume times the density. So we want 1,000 kilogram per meter cubed times 9.8. Gives us newtons per meters cubed. Times the volume in meters cubed gives us total newtons, or the force of that thing. And then the work then is the little bit of work is this whole thing, the force, which is negative 0.8x plus 1 times 2 times delta the volume times the weight density, then times the distance it has to go. And the distance it has to go, I've made my frame of reference x, so just times x. So that is our little bit of work. And it's going to go from what to what? The integral will go from 0.25 to 0.5, right? The top layer of water is at 0.25 meters. Half of 50 centimeters would be 25 centimeters. So from 0.25 to 0.5 meters, that's your little bit of work. This is times, not minus. If you got a question, you can ask on the way out. I'll leave it up. I won't take it down. Okay, so we'll have written quiz on Monday and web work. Oh no, web work will be Wednesday, written quiz Monday. Web work will be Wednesday. You too. I see you got that one that on their first try after not knowing what to do.
Yeah, I really I didn't sleep. I was watching the videos.
Oh my gosh.
Yeah.
Jeez.
I'm so excited right now.
Oh, good. Oh, you did well on the quiz.
Yes.
Good.
I'm so happy right
Good.
now.
Good.
So, we go to bio.
All right.
Take care.
Have a good weekend.
I know why we need to multiply the 1,000 kilogram per.
What's that?
That 1,000. Why we need to multiply that?
By 9.8?
No, that 1,000. I mean the Soundness.
Because that's volume.
Yeah.
We need force. So the force is going to be the weight density times the volume.
I get that.
So we need that in newtons. We need force is going to be the amount of newtons.
Okay.
So 1,000 kilograms per meter cubed is the mass density of water.
Okay.
Every 1 meter cubed is 1,000 kilograms.
Okay.
So we've got some number of meters cubed times 1,000 will give us a kilogram.
Oh.
And then times 9.8 will give us a newton.
Yeah, but now we're using the centimeter, so we need to
No, meters. I changed everything to meters.
Oh.
So that was meters.
Okay.
2 is meters, because it's 2 this way.
Okay.
And then this is all meters now. So that whole thing is all in meters.
Okay. Mine is the number of the interval. It's from where? It's from 0 to 50. It's
No,
from 0 to
because
25.
where's the first layer? The first layer is not at 0, because it's only half full.
Okay.
So the first layer is where?
0.25.
0.25, and then the
2.5.
0.5. That's right.
Okay.
0.25 is the first layer. 0.5 is the bottom layer.
Thank you.
Yeah, you're welcome.
Why did you stop there after the 9800?
Oh, work is force times distance. So that thing is the force. Volume times density gives the force. And this force times distance gives work. And each layer has to go x. Good? Okay.
Thank you.
Yep.